3, 4, 5. So we've actually seen two so far of what are called Pythagorean triplets. A Pythagorean triplet is anytime these three side lengths, A, B, and C, or two side lengths and the hypotenuse. There's 7, 40, 41. No, that's not right. Welcome. So Pythagorean Theorem is what we're looking at today. We are over halfway through chapter 10 as of today when we finish the 10-4 lesson. And we are barreling towards a chapter 10 test that will be coming at some point. I'll talk more about that in the Zoom time. You guys may be interested in the details there. Pythagorean theorem, you might think, well, pretty simple. You know, what else is there to know about the Pythagorean theorem? Haven't we basically got it mastered at this point? You've got a triangle, and it turns out that if you look at that triangle in terms of its side lengths, of course, a right triangle, I should say. Pythagorean theorem is all about right triangles. And if in your side lengths, you've got your two legs, which are always going to be shorter, and you look at literally the square built off of those legs. So a 5 by 5 square here, and then a 12 by 12 square here, all the way over. And then you were to draw a square, right? That's pretty good. And you were to measure the area of this object, you would find that it has an area of 169, which is another way of saying that its side length is 13. And so literally, this first square plus this second square always equals this third square. Of course, we don't normally say it this way. We usually just say a squared plus b squared equals c squared, where a is the first leg, b is the second leg, and c is always the hypotenuse of the right triangle. Another way you could say this, the sum, right? The sum of the squares of the legs of a right triangle will always be equal to the square of the hypotenuse, and that's where the c gets involved. But that's what the a squared plus b squared equals c squared actually means. Of course, what we want to do mainly here is put this into practice. So let's take a look at some of the examples. I'm going to jump right into page 541 in your books. Find the length of the hypotenuse of a right triangle if a is 8 and b is 15. And of course, what they really mean here is that the first side is 8. So I'm actually going to draw a side length of 8. Second side, 15. 3 sets of 5 there. It's a right triangle. And of course, we want to connect that third side nice and straight. So we've got a side length, 8, side length, 15. We want to figure out that third side. A squared plus b squared equals c squared. So in this particular case, we simply plug in the 8 and the 15 for a and b. 8 squared, 64. 15 squared, 225. The sum of those is 289. And it just so happens that the square root of 289 is 17. So this is the 8, 15, 17 right triangle. So we've actually seen two so far of what are called Pythagorean triplets. A Pythagorean triplet is anytime these three side lengths, A, B, and C, or two side lengths and the hypotenuse, however you want to refer to it, come out as integers. There's nothing special about the cases that come out as integers. We just like them because we like integers more than we like irrational numbers. So there's one called the 3, 4, 5, because 3 squared is 9, 4 squared 16, 9 plus 16 makes 25, the square root of which is 5. So your 3, 4, 5 works in the a squared plus b squared equals c squared formula. Of course, you already saw the 5, 12, 13, 8, 15, 17 here. There's 7, 40, 41. No, that's not right. 9, 40, 41, 7, 24, 25. I don't know. There's a weird one with 10. There's obviously the 6, 8, 10. You can take any triple and just kind of multiply. Like in this case, if we just doubled everything, we would end up with the 16, 30, 34 Pythagorean triplets. So you can come up with about as many as you want. Again, there's nothing particularly special about them beyond the fact that they use integers, and of course we love integers. Take a moment and work out Check Your Progress 1A and 1B in your notebooks. All right, so I'm working out Check Your Progress 1A, and I want to pause here. This one is not a Pythagorean triplet, right? 218 is not a perfect square. It's really close to a perfect square. The next perfect square up is 225, and so we could say that C is like 7-ish or 14.8. Let's see how close I got. 14.7 times 14.7, 216. So pretty close. 14.7 is a pretty good approximation. But in this chapter, I want to try and do something a little bit different. I don't want to know that C is approximately 14.7, although that is true. Instead, I want you to take that 218, that root 218, we should say, and I want you to simplify it the way that we did in lesson 10-1. And so in this case, we might do our prime factorization. 2 obviously goes into this. It's 109 times. But if I'm not mistaken, 109 is a prime number. Let's see, does 13 divide 109? No. Yeah, and does 11? No. So 109 is definitely a prime number. So in fact, this does not simplify, and root 218 is just root 218. And that would be my preferred answer for Check Your Progress 1A. Don't approximate it and tell me, oh, well, it's about 14.7. It's fine just to tell me it's root 218. If I want you to approximate it, I will say so. All right, jumping back into Check Your Progress 1B. All right, once again on Check Your Progress 1B, pause if you haven't got the answer yet. But the answer you can see on my screen would be the square root of 136, which is awfully close to 11.5, at 11.6 maybe, but it's not an exact square root, right? It's between 11 and 12. 11 squared is 121, 12 squared is 144. I don't want you to approximate it. I want you to tell me, oh, that's the same thing as 2 root 34, because we can factor it into 4 times 34. 34 doesn't simplify any further. It's 2 times 17. There are no pairs there, but the 4 does. Root 4 is 2, and so that's that. 2 root 34 is Check Your Progress 1B. Now, of course, there's nothing special about having these work out such that you're finding the hypotenuse every time. You can use the hypotenuse to find other side lengths. So that's what's happening here in example 2. We're given another triple. So this time it's pretty tall. Let's just say that looks about right. And we have a side length of 10 and another side length, although it's a special side, it's the longest side, the hypotenuse, 25, and we want to find what they've labeled as A. Well, we can still use Pythagorean Theorem. It's just that this time the thing we don't know is on the left side of the equation instead of the right side of the equation. A squared plus 10 squared would be 25 squared. A squared just stays A squared. 10 squared, though, is 100. 25 squared, 625. Minus 100 this time, minus 100. We got to do a little bit of algebra. A squared equals 525. Take your square root, and we end up with whatever the square root of 525 is. We could approximate this. In fact, the book does. It tells you, oh, that's about 22.91, right? And of course, we're only interested in the positive values because it's a triangle. It's an actual object. It's going to have a positive length. But if we want to, we can also figure this out. This is the same thing as 25 times 21, I believe. Now, 21 would just be 3 and 7, so nothing special happens with that. Nothing pairs up. But 25, of course, has a square root. So we could say A equals exactly 5 root 21. And so that's how we work out for a given side length, one of the smaller sides. Take a moment to work out Check Your Progress 2A and 2B in your notebook. All right, so there are your answers for Check Your Progress 2A and 2B. 2A works out exactly to 4 root 10. That would be approximately 12.6, but again, we don't care about the approximation. Check Your Progress 2B, we get about 17.8, but again, we don't care about the approximation. We get exactly 8 root 5. You'll notice I didn't even write a triangle down for Check Your Progress 2B. Once you get pretty comfortable with these, you don't always need a triangle, though it never hurts. Let's go ahead and work out example 3. What is the area of this triangle with a hypotenuse of 20, triangle ABC, and a base of 12? And again, what we want to know is the area. Well, of course, the area of a triangle is 1/2 base times height. Some of this we already know. We already know that the base of this triangle is 12. So really all we need to figure out is what's the height. Obviously you can tell where Pythagorean theorem is going to come into play here. 12 squared plus h squared equals 20 squared. 144 plus h squared equals 400. H squared equals 256 when we subtract the 144 on both sides. And of course we take our square root, 256 happens to be a perfect square. It's the square root of 16. And so we can take that back up here, and our area is going to be 1/2 times 12 times 16. 2 goes into 12 6 times. 6 times 16 is 96 units squared. And of course, that happens to be answer choice A. A, right? A equals 96 square units. Take a moment and work out Check Your Progress number 3. So I'm actually going to talk through this one because this one's a little tricky. We're given a square and a diagonal, which is the length connecting two corners that are otherwise unconnected in a square, is 70. And then that's it. That's the only information they give us. And so it might feel like, well, how are we supposed to find the sides? Except, although that is the only information they give us, because this is a square, I know these two sides are equal. So where normally I would say a squared plus b squared equals 70 squared, in this case, because the two sides are equal, I could just as easily call that second side a again. And so really a squared plus a squared equals 70 squared. So 2a squared equals, let's go ahead and write this down, 4,900. Divide by 2, you get a squared equals 2,450. Take your square root, and what you're going to end up with, if I think about this is 1225 times 2. I know it's weird. You have no idea how I know this. It doesn't really matter how. And so 1225 happens to be the square root of, or rather the square of 35. And so the exact side length here would be 35 root 2. So a equals 35 root 2. That ends up being approximately 49.5-ish, I think. And so this would have a walkway pretty close to h, 50 meters. So yeah, you could use your calculator to figure that out. All right, last thing to say here is that the Pythagorean theorem, very flexible, works just as easily in reverse. In other words, if you know something is a right triangle, then you can plug the sides in and figure out, say, a third side. A squared plus b squared equals c squared. 3 squared plus 4 squared, you can figure out the hypotenuse has to be 5. That's what we've done all lesson long. But it also works just as easily backwards. If I give you the 3 sides and ask you to figure out whether it's a right triangle, all you have to do is plug them into Pythagorean Theorem. If they work, it is a right triangle. If they don't work, it is not a right triangle. So let's try that here with example 4a, where we are told 20, 21, and 29 are the sides of some triangle. And we want to know, is that a right triangle? Well, if it is, it's going to fit the Pythagorean theorem. Again, the hypotenuse is always the longest side, so that has to be by itself on the other side of the equal sign. But we're just going to figure out, is it true that 20 squared plus 21 squared is 29 squared? Going to our calculator, 20 squared is 400, 21 squared is 441, 29 squared happens to be 841, and so, yes, it turns out there is a 20, 21, 29 right triangle that would look something like this, scaled up, but it definitely is a right triangle. Example 4b, we've got side lengths 8, 10, and 12. And again, we want to know, is this a right triangle? Well, this time when we plug into Pythagorean theorem, 8 squared plus 10 squared, does it equal 12 squared? 8 squared is 64, 10 squared 100, 12 squared 144. No, that is not true. Right? 64 plus 100 is not 144. So it is not a right triangle. Take a look at the side lengths and check your progress for A and for B and tell me whether or not they form right triangles doing the same thing. All right, so you can see my work for check your progress 4A and 4B. 9, 12, 16, no, that is not a right triangle. It gets close, but it does not actually work. 18, 24, 30, yes, that is a right triangle. In fact, that's another Pythagorean triplet because they're all integers, but they definitely do work in your Pythagorean theorem. So that's that. That's lesson 10-4. Hopefully that was helpful to you all. You will have a homework assignment. In fact, I think you already have a homework assignment. So take a look at that and be sure to get back to me with any questions. Thanks for watching. Make sure to like and subscribe below. I will catch you guys later.